Today, we're going to pull back the curtain and make the invisible visible. We're talking about the powerful chemistry that's happening all around you all the time, from the food you eat to the soap on your hands. So think about it for a second. That sour pucker you get from lemonade, right? Or the slippery, almost slick feel of soap on your hands. Or even the relief you get from an antacid tablet after a big meal. I mean, they all seem completely unrelated, but they're all connected by the same fundamental chemistry. In that link, it's an invisible world of acids, bases, and salts. These are like the main characters in a chemical story that's constantly unfolding around us. So today, we're going to make them visible and really understand how they shape pretty much everything. All right, so let's get right into it and meet the two main players in this story, acids and bases. And trust me, they have very, very different personalities, as you're about to see. So how do we even tell them apart? Well, on a really basic level, it actually comes down to our senses. Acids, like in lemons or vinegar, are defined by that sour taste. Bases, on the other hand, like baking soda or soap, are often bitter and have that classic slippery feel. And in a lab, they have opposite effects on this cool little indicator called litmus paper. Acids turn it red and bases turn it blue. A simple but very clear difference. And this isn't just something that happens in a chemistry lab. You've probably seen this yourself. Turmeric, which is in most curries, is a fantastic natural indicator. The moment you scrub a curry stain with soap, which is a base, it flashes this reddish-brown color. It's proof that these chemical rules are at work right in your laundry room. Okay, so now that we've met our main characters, let's see what happens when they actually interact with other things and with each other. This is where the real action begins. So here's our first major reaction. When an acid gets together with a metal, a kind of trade-off happens. The acid starts to dissolve the metal, and in the process, it creates something new called a salt. We'll get back to that. And it releases a bunch of hydrogen gas. And you can see that reaction happening right here in this test tube. See those bubbles fizzing up as the acid hits the zinc? That's not just air. No way. That is pure hydrogen gas being created and released right before your eyes. Pretty cool, huh? Let's check out another one. If you react an acid with something called a metal carbonate, think of things like chalk or even baking soda, you get a salt and water again, but this time you also get carbon dioxide gas. This is the exact reaction behind those classic volcano science experiments you probably did in school. But what about the ultimate showdown, acid versus base? When these two finally meet, it's called a neutralization reaction. And it's exactly what it sounds like. They literally cancel each other out, leaving behind two incredibly simple things, a salt and plain old water. It's like a perfect chemical handshake where both sides win. So we know they react, but here's the thing. Not all acids and bases are created equal. Some are incredibly powerful, while others are pretty mild. So how do we, actually measure that strength? Well, we use something called the pH scale. It's a super useful scale that runs from 0 to 14. A low pH, down near 0, means something is very, very acidic. A high pH, way up at 14, means it's very basic or alkaline. And right there in the middle, at a perfect 7, is neutral. Think pure water. Let's put this into context with stuff you see every day. Lemon juice, super acidic, down around a pH of 2.2. Your morning coffee is acidic too, just not quite as much. And on the other end, you've got common bases like baking soda and milk of magnesia. So you see, this scale isn't some abstract thing. It's in your kitchen right now. So why does any of this matter? I mean, okay, it's cool science, but what's the big deal? Well, let's connect all these ideas to the world we actually live in, every single day. First stop, your own body. Your stomach is basically a pouch full of powerful hydrochloric acid with a pH somewhere between 1.5 and 3.5. That intense acidity is absolutely essential for breaking down the food you eat. It's a perfect example of a strong acid doing a really helpful job. Now let's head up to your mouth. When bacteria in your mouth break down sugars, they produce acid. If the pH in there drops below 5.5, it starts to actually eat away at your tooth enamel. So, every single time you brush your teeth, your basic toothpaste is waging a tiny little neutralization battle against that acid to protect your smile. The stakes get even higher when we look at our whole planet. When rainwater becomes too acidic with a pH below 5.6, we call it acid rain. And when that rain flows into rivers and lakes, that shift in pH can make it impossible for fish and other aquatic life to survive. And even nature uses this chemistry as a weapon. That burning pain you feel from a bee sting or from brushing against a stinging nettle? That's an injection of acid, methanoic acid to be exact, and it's designed specifically to cause pain and irritation as a warning. Now, we've seen that when acids and bases neutralize each other, they create these things called salts. But it turns out, these salts are holding on to one last, really surprising secret. I mean, just take a look at a salt crystal. It seems like the very definition of dry, doesn't it? A solid, perfect little geometric shape. But what if I told you there's actually water hidden inside? Yeah, really. It's because of something called water of crystallization. This is a fixed number of water molecules that get locked right into the salt's crystal structure as it forms. This hidden water is actually what gives many crystals their specific shape, and even their cool colors. And a perfect example of this in action is a plaster cast for a broken bone. Plaster of Paris is basically a salt that's had its water of crystallization baked out of it. So when a doctor mixes that powder with water, it greedily reabsorbs that water, locking the molecules back into its crystal structure and hardening into solid gypsum. It's this simple chemical transformation, the rehydration of the salt's crystals, that provides that rigid support needed to heal a fracture. It's chemistry you can literally feel. So there you have it, from the food you eat, to the soap you use, to the rain that falls from the sky, and even the casts that heal us. It's all one big story of acids, bases, and salts. Now that you can see this invisible world, what are you going to notice tomorrow that you didn't notice today?